Hello and welcome to the talk Power Laws and Popularity. This talk was organized by Accelerate, which is a data science education company in Hong Kong. It was originally scheduled to be held in November 2019, but because of a lot of problems in Hong Kong, it never actually happened. So now I'm giving the talk online. It's meant to be for a general audience, and the original abstract is here. It says, many phenomena can be modeled by a power law, which is a kind of probability distribution. Knowing the theory behind these rich get richer processes will enable you to predict whether your data will follow a power law before seeing it, which will amaze your friends. So I'm hoping that this talk is accessible to people who don't really have a mathematical background. You'll still get something out of it, and hopefully you can amaze your friends. So that's the goal of the talk today. Now I'm going to start sharing the presentation itself. Here we are. Here's the presentation. I'm going to start up by talking about the heights of tall buildings in Hong Kong. So if we took the 500 tallest skyscrapers in Hong Kong and lined them up, then we get a picture like this, where each bar in this picture represents one skyscraper. There are just a few extremely tall skyscrapers, and then there are lots of skyscrapers that are kind of lower in height. There's a long tail of shorter skyscrapers and a few very tall ones. And that turns out to be a pattern that has some mathematics behind it. And in this case, the mathematics is this magic formula here. So what if I told you that the heights of buildings in Hong Kong are actually described by this mysterious magic formula? And the magic formula is something involving x is 1,313,560 million divided by x to the power 5.65. Would you be amazed? Well, not yet, probably, because I haven't told you what this formula actually has to do with the height of buildings and how it should be interpreted. So here's our magic formula and a picture of a magician in the corner here. So I need to tell you what the magic formula does. So the way it works is you put the height of a building as x. So let's say we're interested in buildings higher than 200 meters. We put 200 meters as x in the formula here. And the magic formula will spit out a number. In this case, we'll get 0.131 as the number it spits out. And then if we look at the actual number of buildings which are taller than 200 meters among the 500 tallest buildings that we started with, we find that there are 65 buildings which are taller than 200 meters. And that's 13% of the buildings, or 0.13, which is almost the same number as we got out of the magic formula. So when we put in the number 200 in place of x, the magic formula is telling us the percentage of buildings which are taller than 200 meters in Hong Kong. And this wouldn't be very interesting if it only worked for the number 200, but actually it works pretty well for a lot of, or a large range of possible numbers. Here are some examples. If we want the proportion of buildings which are higher than 250 meters, we put 250 meters into the formula, we get 3.7 as the answer, 3.7% as the answer, and the actual answer is 3.6%. Again, if we look at buildings taller than 300 meters, we find that that's 1.3% of buildings. Oh, sorry, the magic formula gives us 1.3%, and the actual answer is 1.2% of buildings. If we look at, say, 170 meters, then we find that the magic formula gives us 33%, and actually 36% of buildings are greater in height than 170 meters. So it's not quite so accurate for lower heights, but it was quite accurate for very tall buildings. So what the magic formula is doing is when we put the number in place of x here, it's telling us the percentage of buildings that are taller than that number. And it's very surprising to me that this formula exists at all, because the heights of skyscrapers depend on all kinds of things which aren't really describable mathematically. Like, for example, something as simple as laws about how tall buildings are allowed to be will influence how tall they are, right? So it's very odd that there should be this magic formula at all. And what I want to do in this talk is to tell you the secrets behind this magic formula. So the questions I want to answer are, why is there a magic formula like this? How could you have known, if you just knew that I was going to talk about the heights of skyscrapers, that there would be a magic formula? And finally, how can you make your own magic formula, which is a part about amazing your friends, because you can show them your magic formula and hopefully they'll be amazed. So let's just discuss for a moment what kinds of things might not have a magic formula. If we look at the heights of people in Hong Kong, what would happen? Do these behave like the heights of buildings? And is there a magic formula for the heights of people? So if we lined up all the people in Hong Kong and looked at their heights, so now each bar represents one person, they look like this. So this shape looks a bit different to the buildings. It still has some very tall people at the end, but there aren't quite as many extreme outliers. And also at the bottom end, some people are very short, but there aren't a huge number of people who are much shorter than the tallest people. So look at this shape and then go back and compare it with the shape from the earlier slide. You can see it's a bit different. So is there a magic formula for this? And the answer is yes, there is a magic formula for the heights of people. And if you look at the number of people taller than X centimeters, roughly you can get it by this formula here, which is the area under a particular mathematical function from X to infinity, or X and above. And here, mu and sigma are certain statistical numbers. Mu is the average height, sigma is the standard deviation of people's heights. So this is a very amazing magic formula, actually. And it's extremely impressive, but it's not as simple as the magic formula for the heights of buildings. And also, it's a bit different in character. So the magic formula for the height of buildings that we looked at is just a number divided by a number to the power of another number. Whereas this one here has a complicated looking mathematical function in it. So although it's a very beautiful formula, it's not quite as approachable. Not quite as simple, I would say. Now, another thing that I would like to say is, well, I think it's remarkable that there's a magic formula for the height of buildings. The existence of a magic formula for the heights of people is maybe not quite as amazing. Why? Well, because the heights of people are largely determined by genetics, right? And genetics is based on genes, and genes have some kind of mathematical structure behind them. So I would say for the heights of people, you might kind of expect that there would be some mathematics that would describe the heights of people. But the heights of buildings, it doesn't really make sense to me that there would be a simple mathematical pattern behind that. And that's why I find it very surprising. So the kind of pattern we're looking at in this talk is a power law, and a power law is defined like this. A quantity follows a power law if the proportion or percentage of items which are greater than X is given by a formula like C divided by X to the A, where C and A could be anything. So a number C divided by X to the power of a number A. And that's basically a power law. So it's a lovely, simple formula. A technical note here, usually you say a quantity follows a power law if it's only true when X is big. So you're usually looking just at big values of a quantity. So for example, in the case of buildings in Hong Kong, we looked at the 500 tallest buildings and we showed that there was some kind of pattern behind that. But that pattern wouldn't necessarily hold if we looked at shorter buildings as well. We did see that when we put smaller numbers into the formula for X, it wasn't so accurate, and that would get less accurate as the heights got lower. So usually, yes, question.
So if just now during the building demonstration, you use the height of the buildings. How about if I change the height of buildings to number of stories?
Okay, number of stories instead of heights in meters. That's a good question, actually. So I think you would see a similar pattern, but it would be, instead of a height in meters, which is a continuous quantity that can have any value, essentially, you'd only be allowed to have fixed value, like 1 story, 2 story, 3 stories. So there's a similar kind of pattern in that case that you can have called a discrete power law, but it's slightly different. So that's basically the answer to your question. If you look at stories instead of heights in meters, then you would be looking at discrete power laws instead of continuous power laws. And I would say these discrete power laws are slightly more complicated mathematically. So that's why I stuck to this simpler kind in this talk.
Thank you.
But it's a good question, thank you. So there we go. Technically, a quantity only follows a power law if it's true if this formula holds just for large values of x. I don't want to get into that too much in this talk, though. And what power laws look like qualitatively is that they tend to have what's called a long tail of very small values, and then a few very large values, like we saw for skyscrapers. Now, this famous power law expert, Aaron Close, said this very nice thing in a lecture in 2011. This is a direct quote from his paper. He said, "Consider a world where the heights of Americans were distributed as a power law. In this case, we would expect nearly 60,000 individuals to be as tall as the tallest adult male on record at 2.72 meters. Further, we would expect ridiculous facts, such as 10,000 individuals being as tall as an adult male giraffe, one individual as tall as the Empire State Building, 381 meters, and 180 million diminutive individuals standing a mere 17 centimeters tall." And so what you're seeing there is that there's a long tail of very small values, in this case, 17 centimeters, sorry, and a few extremely large values. And that's characteristic of power laws. And this is exactly the example we saw that doesn't hold for human heights. So there is a pattern for human heights, but it doesn't have these extremely tall people and a large number of extremely short people. So that's the difference between power laws and other kinds of mathematical laws that you might see. So what characterizes power laws is that they have a long tail and a few large outliers. Here are some examples of power laws in nature. So if you look at the sizes of towns, you have many villages and a few enormous cities, like Hong Kong, in fact, and they tend to follow a power law distribution. If you look at the number of species in different families of biological organisms, you tend to get power laws. People's incomes, some people are obscenely wealthy, a lot of people are very poor. They follow a power law called Pareto's law, which is well known from economics. The number of friends people have in a social network, some people have a huge number of friends, most people just have a few. The frequency of word use in text, this is known as Zipf's law. The number of citations of scientific papers, number of casualties in wars, the sizes of earthquakes, upvotes in Reddit threads, popularity of books, and so on. So an awful lot of things that you see in the real world approximately follow a power law. But you have to be careful. Although I said that power laws are characterized by the properties of having a long tail and a few outliers, not everything with a long tail and a few outliers is actually a power law. So sometimes you can distinguish between a power law and something that looks a bit like a power law superficially, but is better fitted by some other statistical pattern. Now I want to move on to how can you recognize whether something is a power law. And one way to do this is to look at the magic formula we had. So the proportion of things that are bigger than x is c divided by x to the a, and apply logarithms. Now logarithms, hopefully you saw them at some point in your mathematical education. They're things that undo powers. So the logarithm of a number is roughly the number of times you have to multiply 10 together to make that number. So for example, to get 100, you do 10 times 10. So you're multiplying 10 with itself twice. So the logarithm of 100 is 2. And that also works for every other number, even if it's not the power of 10. So if you're not familiar with logarithms, you can think it roughly as taking the number and giving you something like the number of digits that make up that number minus 1. So for example, for 100, it's 100, so that's 3 digits. Minus 1 is 2. The logarithm of 100 is 2. But what's interesting about logarithms is that they undo multiplication. So if you have division, it turns into a minus. And if you have a power, it turns into a multiplication by the number that was in the power. So when you apply logarithms to this equation here, you get log of the left-hand side, log of the proportion of things that are greater than or equal to x, becomes log of the number c minus a times log of x. And the reason why we want to do that is because suddenly we've got a straight line, right? This is the formula for a straight line. It's a number times log of x plus another number. So y equals mx plus c, if you remember that from high school mathematics. And so instead of doing some curvy plot, we can plot these numbers that are supposed to appear in a straight line. So what we plot is we plot the logarithm of the proportion of things that are greater than or equal to x on the y-axis, and the logarithm of x on the x-axis for each value of x that we see in our data. And then we have these points, and if we have a power law, then these points have to follow a straight line. So this is what I did for the 500 tallest buildings in Hong Kong, and the picture I got was the picture that you see there. Each one of these gray dots represents one building. And on the x-axis, I've got the logarithm of its height in meters. On the y-axis, I've got the logarithm of the percentage of buildings that are bigger than or equal to that one in height. And roughly, I've got a straight line, and that's how I know that this is a power law. And then I can fit line of best fit. That's the red dotted line. You could do that in Excel, for example, using linear regression. And from that, I can read off the numbers that I got for C and A. So I got log of C is 2.118, and A, that's the power, is 5.65. And then that's how I got the magic formula. So remember the magic formula for the height of buildings. Those numbers there in the magic formula that looked very mysterious at the beginning are actually coming from this straight line that I fitted to the data. So there we go. Now, a footnote that I should say is that it's important that this technique, although it's widely used in physics and other fields, it's not the best way of getting a power law fitted to your data. And if you want to read more about that, you can read the paper by Closey, Shalizi, and Newman, I think it is, that I've cited at the bottom of this slide here. That's a very important paper with many citations because it explains why this isn't the best way to fit a power law. But I don't want to get into those technicalities today, so I'll just leave it here. This is how you can find a power law to fit your data. So the questions we wanted to answer, we've already answered. Why was there a magic formula? There was a magic formula because I made this plot and I saw that it was a straight line. And then that's how I found my magic formula. And you can make your own magic formula by doing the same thing with whatever data you want. But one question remains, which is, how would you choose your data set in the first place? How would you have known in advance that there was a magic formula? How would you have guessed that if you make this plot, then it's going to be a straight line? And that's what I want to talk about in the rest of this talk. Where do power laws come from? Why are power laws so common? How could we know in advance that there would be a power law in our data? And one way you can get power laws is by a so-called rich get richer process, which is also called a Yule process, named after this person, George Udny Yule, who is a famous statistician. This is a picture of him from Wikipedia. And the way these work is, well, we'll do an example of a Yule process operating. So suppose we start with 10 individual people, and a new person arrives and randomly chooses a person to make friends with. So now you have one group of 2 people who are friends, and you have 9 groups consisting of 1 person. So these are people with no friends. And now suppose that people keep coming to this group where there are now 11 people, and they want to make a friend with somebody, and they choose to make friends with a particular friendship group based on how many people are in it already. So that means that the next person is twice as likely to choose to join this green group because it's already got 2 people in it compared to any of the other groups. And as you keep doing this, you end up with people clumping together into large friendship groups. So some friendship groups get larger, but other ones remain small. And the larger a group gets, the more likely it is to get more people to join it because it's bigger. And this is called a rich get richer process. And after 100 people have joined, for example, we've got these group sizes. So there's one group of 32 people that got quite big, 2 groups of 20 and 19 that got fairly big, and then quite a larger number of groups that are much smaller, with only a modest number of people in. So this 32 people, that would be the clique of popular kids. Then you have some groups here that are fairly large, and then a lot of people who are sort of smaller groups, I should say. So that's a rich get richer process in operation. And I simulated this for 100 steps, and then I looked at the data. And you can see if you do a power law plot for this data, just like we did for the heights of buildings, roughly you get a straight line, and you can fit an equation to the straight line like I did before and get your power law relationship, which will tell you, remember, this is your magic formula here, which will tell you the proportion of people who are, the proportion of groups of people in this case, which are bigger than or equal to size X when you plug X into this magic formula, just like we did for the heights of buildings. And it's a theorem that whenever you have a rich get richer process operating like this, then it will tend, after running for a long time, to give you a power law. So that's a shortcut to figuring out whether something is a power law, because if you have a bunch of things and those things grow in proportion to how large they already are, then their sizes will tend to follow a power law. And examples of things that do that are population, like the populations of towns and cities, and popularity, like the popularity of Reddit comments or the popularity of people on Facebook, maybe. So an easy way to remember what follows a power law is that population and popularity will tend to follow power laws, which is why I called the talk Power Laws and Popularity. So now we can explain some of the reasons why some things follow power laws. For example, the sizes of towns and cities. If you imagine a new person joining a town or city to look for work, they're going to be more likely to find work in larger cities. So you have a rich get richer situation. For incomes, rich people literally get richer because they have more money to invest, I guess. So that's why incomes tend to follow a power law. Number of friends on a social network, I guess you tend to go with more popular people to befriend. So that would follow a power law. Citations of scientific papers, the more popular papers get more cited, and then people see the citations and read those papers. So those citations are going to follow a power law. Number of casualties in wars, well, this is a bit harder to explain, but I guess one example is that the more people have already been killed in a war, the more people are likely to be killed, because I guess the countries that are involved have more invested in it, and there's a kind of sunk cost situation where they don't want to stop fighting when they've already been fighting for a while. Something like that maybe explains why the number of casualties in wars would tend to follow a power law. Now, this Yule process doesn't explain every kind of power law, and here are some examples of ones where I don't think this rich get richer idea really explains why these would follow a power law. So the sizes of earthquakes, I don't really understand the science behind this. So I don't know why those would follow a power law necessarily. Building heights, which is the example I led with in this talk, I'm not completely sure why it would follow a power law. Maybe you could think of it as kind of related to population size in different districts, but that explanation seems a bit nonsensical to me. I don't see why that would follow a power law. And word frequencies, I don't really see a rich get richer process in operation. I guess maybe over time, if people are using the language and they see a word used a lot, they might then know that word and be more inclined to use it. That might kind of make sense, that that would be a rich get richer process, but not necessarily. So you can get a power law without having a rich get richer process. It's just that these rich get richer processes are a fertile source of power laws. Now, I want to do one more example, and the reason why I chose this example of fighter pilot kills is partly because it's an example of a power law that I've heard of before, and I thought I would like to test it out, and partly because this talk was originally scheduled for November the 11th, which is the anniversary of the end of World War I, so I thought I would put an example that has to do with World War I. So for World War I fighter pilots, there's there's data on how many people they shot down, and you expect that the more planes somebody has already shot down, the more experienced that pilot would be and the better they would get at shooting down more planes. So you'd expect some kind of rich get richer process to be in operation. So you'd expect this data to follow a power law. I plotted it. Well, I only had the data for people who shot down 5 or more planes, which is fine, because remember that power laws are only supposed to hold for large values of the quantity you're looking at. And I plotted it, but in this case, I didn't see a straight line. I saw a kind of kink here. So I wouldn't say this data is following a straight line. It doesn't look like a power law to me. But maybe if you look beyond a certain point, like beyond the point where this line bends, then that could be a power law because that's kind of straight. So sometimes if you just look at large values of your quantity, you might see a power law relationship which doesn't hold in the rest of the data. So I looked at the 118 top pilots, just like we looked at the 500 tallest buildings at the beginning. And then I fitted a power law to that and found, indeed, it was a fairly good fit with a power of 3.6 in this case. But in this case, I would be reluctant to say that the original data follows a power law because it's clearly not a straight line. So there's something else going on here, and maybe it would be possible to find a statistical pattern that wasn't a power law that fits this data better based on some simulation or modeling. And then the other example I wanted to share is from a book called Networks, Crowds, and Markets by Easley and Kleinberg, which I recommend reading. It's very good and it's available online for free because of the generosity of the authors. So they have a question from their chapter on power laws, which again, I think is recommended reading. And this is an interesting challenge question, which I intend to use as an audience challenge at the end of my talk. So it says, suppose that some researchers studying educational institutions decide to collect data to address the following two questions. A, as a function of X, what fraction of Cornell classes have X students enrolled, Cornell being a university in the US? And B, as a function of X, what fraction of third grade elementary school classrooms in New York State have X pupils? Which one of these would you expect to be a power law or be closer to a power law? And you can answer this question using the ideas from this talk. So maybe if you want to do it as a challenge, you should pause the video and then I'll give you my suggested answer. Actually, audience, what do you think, A or B?
Let me see again. Well, A, please.
A, yes, I agree with you. I think A is the correct answer. And the reason why is because I would say that in a university, students have a choice of what classes they go to. So there are going to be more popular classes and less popular classes. And the more popular classes are going to be really big, and then the less popular classes are going to be smaller. That might not be true in your first year where you have a lot of compulsory classes, but I think in general, you'd expect that situation to be closer than a power law, closer to a power law than the situation of elementary school classrooms, where the classes are likely to be more fixed in size because there'll be laws about how big a class can be, and everybody is studying the same things. So people can't choose to go to different classes in elementary school. And for that reason, I would expect that situation A would be much closer to a power law than situation B. So what I'm saying is, in conclusion, that in situation A, in a university, I would expect that class sizes would be more likely to have a get richer process underlying them, and therefore that would be more likely to be a power law. That's my answer. So that's correct. Well done.
Thank you.
And I believe that's the end of the talk. So you can ponder on these things. So if a get richer process is in operation, you only need to get a tiny bit lucky in the beginning in order to end up very rich indeed at the end, like we saw with these friendship groups where you just had 10 individual people, then suddenly one person joined one group at random, and that group was then bigger, and then that made it get bigger and bigger and bigger. It's kind of snowballed until it was size 32. So maybe this explains why some people or startups or sports teams or publishers or search engines or politicians are very successful, while many other people try and do these things and they fail because not because they were worse at it than the big ones, but because in the very beginning, they didn't have that lucky break that made it work for them. So maybe that guides you, to be one of these people who start a lot of companies until they get one that's successful just by random chance. Maybe that's the right strategy. So there are some things to ponder from this power law stuff and the idea of get richer process. And there's lots more that could be said about it, but I just wanted to keep this talk fairly short. So thank you very much for attending, and goodbye.